In this video, we'll start talking about the reactivity of aldehydes and ketones. We'll start off by telling you how to name these things in a very sort of simple way. Then review reactions that we already know to make aldehydes and ketones. And then briefly introduce the idea of addition reactions to aldehydes and ketones under acidic and basic conditions. Okay, so how do you name aldehydes? Well, what you do is you drop the ane suffix. So instead of butane, now it's butanal. So you drop the E and you add an Al for aldehyde. So it's a 4-carbon hydrocarbon is called butane. A 4-carbon aldehyde is called butanal. You don't have to specify the position of the aldehyde. It's always on the end, because remember what defines an aldehyde is the presence of a hydrogen on the end of the carbon-oxygen double bond. Some common names for aldehydes: formaldehyde is a 1-carbon aldehyde, acetaldehyde is a 2-carbon aldehyde, and we've talked about benzaldehyde already. You might want to be familiar with these names. For ketones, it's a little bit more complicated, right? Because a carbon-oxygen double bond could be on any of the middle carbons, so you could have 2-heptanone or 3-heptanone or 4-heptanone, and so in that case you do need to specify the position of the ketone by 3-heptanone or heptane-3-one. Either one is acceptable, but for butanone, since there's only one possibility, you just call it butanone, not 2-butanone. That's redundant. We're not going to worry too much about naming. And some common ketones that you might have heard of before: acetone is one of the simplest ketones, acetophenone, benzophenone. Okay, so let's review some reactions that we already are familiar with to make aldehydes, right? One reaction that we already know is oxidation of primary alcohols, right? If you have a primary alcohol, that means the carbon's only bonded to one other carbon. We've already said PCC will oxidize that to the aldehyde stage and it will stop. So we know one reaction to make aldehydes, that is oxidation of a primary alcohol. Another reaction that we're familiar with is ozonolysis of alkenes, right? Let's say we took this alkene and treated it with ozone and a reducing agent in the second step, like dimethyl sulfide. What we get, remember, is we break the double bond and we replace each carbon that was in the double bond becomes a carbon-oxygen double bond. So in this case we get 2 aldehydes, we get formaldehyde, and we get propanal. The last reaction I'm not going to really spend a lot of time talking about. This was something that we skipped in reactions of alkynes, which we didn't really talk about. But you can understand hydroboration of alkynes very similar to hydroboration oxidation of alkenes, right? Let's say we treat this with borane, BH3, and hydroboration oxidation, H2O2, right? Remember, the boron goes on the less substituted carbon and the hydrogen goes on the more substituted carbon. We got 1, 2, 3, 4, 5 carbons here, so we get this thing which is called an enol. And what we're going to learn later is that enols are much, much more stable in their tautomeric form. A tautomer of an enol is an aldehyde, and so this actually prefers to exist in its aldehyde form. So there's an equilibrium here which strongly favors the aldehyde, which we'll talk about more. So hydroboration, oxidation of alkynes, ozonolysis of alkenes, or oxidation of primary alcohols will give us aldehydes. Similarly, we can look at reactions that we're already familiar with to make ketones, right? We can oxidize secondary alcohols. Let's say we had this secondary alcohol, Jones oxidation, so chromium trioxide, sulfuric acid, and water will oxidize this to the ketone, so we'll PCC. You could get the same ketone if you did ozonolysis of this alkene. So remember, just depending on what's bonded to the carbon, you might get an aldehyde or you might get a ketone. So ozonolysis of tri-substituted and tetra-substituted alkenes will give 2 ketones in this case. Hydration of alkynes is very similar to the hydration of alkenes, right? Remember, acid and water. The OH goes to the more substituted carbon, the hydrogen goes to the less substituted carbon. So now we get an enol, which will rapidly tautomerize to the ketone. Friedel-Crafts acylation we just got done talking about. We know that if you take benzene and react it with acetyl chloride and aluminum trichloride, get a ketone. So there's 4 ways to make ketones. Oxidation of secondary alcohols, we've already talked about that. Ozonolysis, we've already talked about that. Friedel-Crafts acylation, which we've talked about, and the new reaction, hydration of alkynes. Okay, so now that we know how to make ketones and aldehydes, let's talk about the reactions that they undergo. And we can rationalize the way that ketones react by looking at their structure, right? Remember that all ketones contain a pi bond between 2 different atoms and have a resonance structure that places a positive charge on a carbon. And similarly, the oxygen is more electronegative than carbon. So this carbon is going to have a positive charge, and it's going to want to be attacked by a nucleophile. So the carbon of all ketones and aldehydes is a good electrophile, and that's going to get attacked by a nucleophile to generate what we call a tetrahedral intermediate, right? The 2 R groups used to be on our ketone or our aldehyde. We have an oxygen, and this is a sp3 hybridized carbon now that it's gotten attacked by a nucleophile. When a nucleophile attacks, in order to accommodate that bond, we need to break the pi bond to generate these tetrahedral intermediates that we're going to see over and over and over again in this chapter. Okay. So if we think about electrophilicity, what's going to make a ketone more electrophilic is less electron donating groups, right? A ketone has 2 R groups which can both stabilize a positive charge, right? So ketones are less electrophilic. Aldehydes are more electrophilic because there's only 1 electron donating group. If you put electron withdrawing groups, you're going to make it even more electrophilic. So ketones, less electrophilic, aldehydes, more electrophilic, and that just has to do with the number of electron donating groups that are attached to that carbonyl carbon. Okay, so when we're looking at the reactions that ketones and aldehydes undergo in the presence of nucleophiles, the first thing that you want to ask yourself is, are we under acidic conditions or are we under basic conditions? Because that determines the first step of the mechanism, which is going to basically determine the entire rest of the mechanism. So let's say we take this aldehyde and treat it with sodium hydroxide and water, right? Sodium hydroxide is a base. It's also a very good nucleophile. So by itself, it's strong enough to attack the carbon of our aldehyde and break the pi bond. Remember, just like in the SN2 reactions, sodium hydroxide is a strong nucleophile. It's going to act as a nucleophile by itself without any help. And so the first step in all basic mechanisms is going to be nucleophilic attack to generate a tetrahedral intermediate, right? So this is nucleophilic attack. Right? If we're under acidic conditions, though, let's say we have H plus H2O, right? Water is not a good nucleophile. And so what we need to do is increase the electrophilicity. We need to make our aldehyde into a better electrophile. So what we do first is proton transfer, which activates the carbon towards nucleophilic attack, right? Because now we have a positively charged oxygen, which has a resonance structure that places a positive charge on the carbon, but our oxygen is now neutral in that resonance structure. So now, in a second step, we get nucleophilic attack. In this case, if water is our nucleophile, now this thing is a good enough electrophile that water can attack it directly. So every single time you look at one of these mechanisms, you want to ask yourself, are you under basic conditions, in which case nucleophilic attack happens first, or are you under acidic conditions, in which case protonation happens first and then nucleophilic attack? So under this, so for example, let's say we've already looked at the reaction, like a Grignard reaction, right? So if you have methyl magnesium bromide, that's a really strong nucleophile. We're under basic conditions, so nucleophilic attack is going to happen first, followed by protonation in a second step with a molecule of water. Under acidic conditions, hydrochloric acid can add across a carbon-oxygen double bond, right? But the first step is going to be protonation of the oxygen, right? So we have protonation of the oxygen to form this intermediate which then undergoes nucleophilic attack by the chlorine atom to form the product of addition. This is just like addition to a carbon-carbon double bond. So these are the nucleophiles that we're going to look at in this chapter. The next video is only going to be covering oxygen-containing nucleophiles. The next video will be sulfur and nitrogen-containing nucleophiles, and the fourth video will be hydrogen and carbon-containing nucleophiles. When you're looking at all of these mechanisms, remember, keep asking yourself, am I under acidic conditions or am I under basic conditions? So to summarize, aldehydes contain a carbon-oxygen double bond that's bonded to a hydrogen and a carbon, whereas ketones have a carbon-oxygen double bond that's bonded to two carbons, right? We know reactions to make aldehydes, we know reactions to make ketones, and what we want to do is when we look at reactions that ketones and aldehydes undergo, we want to ask ourselves, is it under acidic or basic conditions? Under basic conditions, we get nucleophilic attack right away, and under acidic conditions, we get protonation first before nucleophilic attack.